3.6. The chain rule. The outline of this video is as follows. We will begin by discussing the core concept of composite functions, which are essentially functions nested inside of other functions, and the unique challenge they present for differentiation. Next, I will introduce the fundamental solution to this problem, the chain rule. We will carefully go over its formal theorem, but I will also provide some intuition to help you grasp why it works on a deeper level. To make this powerful rule easier to apply in practice, we will then learn a simple and effective method called the outside-inside rule. From there, we will specialize to a very common pattern known as the power chain rule. To bring all these ideas together, we will finish by working through several key examples and applications, ensuring you feel confident using the chain rule in various contexts. So far, we have learned rules for differentiating many types of functions, but what happens when one function is nested inside another? To handle this, we need a method for what are called composite functions, which are essentially functions of a function. For our motivating example, f of x equals sine of the quantity x squared minus 4, we can see it is built from two simpler pieces we already know how to differentiate. There is an outer function, y equals sine of u, and an inner function u equals x squared minus 4. The key question is how to combine the derivatives of these individual pieces to find the derivative of the whole expression. This is precisely what the chain rule allows us to do. It provides a straightforward method, stating that the derivative of the composite is the product of the individual derivatives. In short, the chain rule is our essential tool for differentiating functions that are built in layers. To build our intuition for the chain rule, let us see how rates of change multiply for nested or composite functions. We can look at the simple linear function y equals 3/2 x. This can be broken down into two linked pieces, an outer function y equals 1/2 u, and an inner function u equals 3x. Now let us examine their individual rates of change, which are their derivatives. The overall rate of change of y with respect to x, written dy dx, is 3/2. Meanwhile, the rate of change of y with respect to u is 1/2, and the rate of u with respect to x is 3. Notice that the overall rate is just the product of the individual rates, since 1/2 times 3 equals 3/2. This is like a gear train. If y changes half as fast as u, and u changes 3 times as fast as x, it makes sense that y ultimately changes 3/2 times as fast as x. So for composite functions, the overall rate of change is the product of the individual rates. Let us see how the chain rule works in practice by applying it to an example and then verifying the result with a method we already know. Our function is y equals the quantity 3, x squared plus 1, all squared. We can treat this as a composite function where the outside function is y equals u squared and the inside function is u equals 3x squared plus 1. Applying the chain rule, dy dex is the product of dy du and du dex. This gives us 2u times 6x. A crucial step is to substitute the expression for u back in terms of x, which results in 2 times the quantity 3 x squared plus 1 all times 6x. This simplifies to 36x cubed plus 12x. Now to verify this, we can first expand the original function, which gives 9x to the power of 4 plus 6x squared plus 1. Differentiating this polynomial term by term gives us the exact same result. This confirms the chain rule is a correct and powerful method for differentiating composite functions. Here we have the formal statement of the chain rule, which is our essential tool for differentiating composite functions. The rule states that the derivative of a composite function, f of g of x, is the derivative of the outer function f, evaluated at the inner function g of x, all multiplied by the derivative of the inner function g. In Leibniz's notation, this idea is expressed very intuitively. If y is a function of u and u is a function of x, then the derivative of y with respect to x is simply the product of the individual rates, dy du times du dx. This is just like our gear example, where the overall rate of change is the product of the rates at each step. Be careful not to forget to multiply by the derivative of the inner function, as that is a very common mistake. The core idea to remember is that the derivative is the derivative of the outside function times the derivative of the inside function. I want to walk you through an intuitive but incomplete proof of the chain rule to highlight a subtle but important detail. The argument begins by writing the rate of change, delta y over delta x, as the product of two other rates, delta y over delta u times delta u over delta x. Algebraically, this seems fine. The next step is to take the limit as delta x approaches 0, which appears to yield the chain rule formula, dy over du times du over dx. The problem here is that this argument implicitly assumes the change in u, which we call delta u, is never 0. However, for an inner function that oscillates, it is possible for delta u to be 0 even when delta x is not 0. In that scenario, our initial fractional expression would involve division by 0, which is undefined. This is why a fully rigorous proof must use a different method to avoid this specific issue. Let us apply the chain rule to a practical problem, finding the velocity of an object from its position function. We know that velocity is the derivative of position with respect to time, which we write as dx dt. Here, the position function, x of t equals cosine of the quantity t squared plus 1, is a composite function. We can break this down into an outer function, x equals cosine of u, and an inner function, u equals t squared plus 1. The derivatives of these separate parts are dx du equals negative sine of u, and du dt equals 2t. According to the chain rule, we multiply these two derivatives together, which gives us negative sine of u times 2t. The crucial final step is to substitute the expression for u back into the result. This gives us the final velocity as a function of time, negative 2t times the sine of the quantity t squared plus 1. To make the chain rule more practical, I like to use what we call the outside-inside rule, which provides a clear, two-step process for these derivatives. First, we differentiate the main, or outside, function while keeping the inside function completely unchanged as its input. Second, we multiply that entire result by the derivative of the inside function. For example, to find the derivative of the sine of the quantity x squared plus x, our outside function is sine, and its derivative is cosine. We evaluate this at the original inside, which gives us cosine of the quantity x squared plus x. Then, we multiply this by the derivative of the inside part, which is 2x plus 1. It is essential to leave that inside function alone during the first steps. The process is to simply work from the outside in, multiplying by the derivative of each new layer. Now we will see how to apply the chain rule multiple times, which is necessary for functions that are nested within each other. Let us find the derivative of g of t, which is tangent of the quantity 5 minus sine of 2t's. We start with the outermost function, tangent. Its derivative is secant squared, evaluated at the original inside function. Then, we multiply by the derivative of that inside part, which is 5 minus sine of 2t's. This step requires a second use of the chain rule. The derivative of 5 is 0, and the derivative of negative sine of 2t is negative cosine of 2t's times the derivative of its own inside function, 2t's. The derivative of 2t is simply 2. Multiplying all these pieces together gives us our final answer. negative 2 times cosine of 2t times secant squared of the quantity 5 minus sine of 2t's. The key is to work from the outside in, applying the rule at each nested layer until you are done. A very common and powerful application of the chain rule is the power chain rule, which gives us a simple recipe for finding the derivative of any function raised to a power. It is a direct consequence of the general rule for an outer function of the form u to the power of n. The process has two main steps. First, you apply the standard power rule to the outside expression, which gives you n times the inner function you raised to the power of the quantity n minus 1. Second, you multiply that entire result by the derivative of the inner function u with respect to x. For example, to differentiate the quantity 5x cubed minus x to the fourth, all raised to the seventh power, you first bring the 7 down in front and reduce the exponent to 6. Then, you multiply that by the derivative of the inside, which is 15x squared minus 4x cubed. The essential pattern is to differentiate the outer power, then multiply by the derivative of the inner function. I will now apply the power chain rule to two more functions to show its versatility. First, to find the derivative of 1 over the quantity 3x minus 2, I will rewrite it as the quantity 3x minus 2 raised to the power of negative 1. Applying the rule, I bring down the power, negative 1, reduce the exponent to negative 2, and multiply by the derivative of the inside, which is 3. This simplifies to negative 3 over the quantity 3x minus 2 squared. For the second example, sine to the fifth power of x, it is important to remember this means the entire sine of x is the inside function raised to the fifth power. So the power 5 comes down in front, leaving sine to the fourth power of x, and then I multiply by the derivative of the inside, which is cosine of x. These examples show how rewriting an expression is often the key to applying the rule correctly. Let us use the chain rule to find a general formula for the derivative of the absolute value function, which is a great example of handling a function with a sharp corner. The key insight here is to rewrite the absolute value of x as an equivalent expression that is differentiable, the square root of x squared. I will express this as the quantity x squared raised to the power of 1/2. Now, applying the power chain rule, I take the derivative of the outer function, giving me 1/2 times the quantity x squared to the power of negative 1/2. Then, I multiply this by the derivative of the inner function, x squared, which is 2x. After simplifying, the 2's cancel, and the expression becomes x divided by the absolute value of x. This result makes perfect sense if you picture the V-shaped graph. For any positive x, the slope is a constant one, and for any negative x, the slope is a constant negative one. So, by cleverly rewriting the function, we can find its derivative for all points except for the non-differentiable point at 0. Let us use the power chain rule to prove a property of a function, that the slope of any tangent line to the curve y equals 1 over the quantity 1 minus 2x cubed is always positive. First, I will rewrite the function with a negative exponent, making it y equals the quantity 1 minus 2x to the power of negative 3. To find the derivative dy dx, the rule tells us to take negative 3 times our quantity raised to the power of negative 4, and then multiply by the derivative of the inside part, which is negative 2. Simplifying this, the negative 3 and negative 2 multiply to give a positive 6 in the numerator. The denominator becomes the quantity 1 minus 2x raised to the power of 4. Since any non-zero number raised to an even power is positive, and 6 is positive, the entire fraction must be positive. Therefore, the slope of the tangent line is always positive wherever the function is defined. Let us use the chain rule to see why our standard derivative formulas for sine and cosine require angles to be in radians. To find the derivative of the sine of an angle measured in x degrees, we first have to convert the angle to radians using the relationship that x degrees equals the quantity pi times x over 180 radians. Applying the chain rule, we differentiate the outer sine function, which gives us cosine of the original angle, but then we must multiply by the derivative of the inner part. The derivative of pi times x over 180 is just the constant factor pi over 180. This means the derivative of sine of x degrees is not simply cosine of x degrees, but is instead that constant pi over 180 times cosine of x degrees. This extra factor would complicate calculations, especially with repeated differentiation. Therefore, using radians is standard practice because it keeps our derivative formulas clean and simple. Let us summarize the chain rule, which is our fundamental method for finding the derivative of a composite function. We have two main ways to express this rule. The first, using prime notation, is the outside-inside rule. The derivative of f of g of x is f prime of g of x times g prime of x. This means you differentiate the outer function while leaving the inner function alone, then multiply by the derivative of the inner function. The second form uses Leibniz notation, stating that if y is a function of u and u is a function of x, then dy dx equals dy du times du dex. A crucial and very common application of this is the power chain rule, which states that the derivative of a function u raised to the power n is n times u to the power of n minus 1, all multiplied by du dex. Mastering these forms is essential for differentiating more complex functions. Let us wrap up by applying the chain rule to a couple of problems that test the key ideas we have covered. The first question asks for the derivative of cosine cubed of 4x, which requires you to use the chain rule more than once. To solve this, you must identify the three nested layers of the function. The outermost layer is the cubing operation, the middle layer is the cosine function, and the innermost layer is the linear function 4x. The second question, about the derivative of cosine of x degrees, is a great reminder that our standard differentiation formulas for trigonometric functions require the angle to be in radians. As we saw with the sine function, you will first need to convert degrees to radians, which introduces a constant factor into the final derivative. Successfully solving these problems shows you can identify all the nested functions and correctly handle the units,